Hello, everyone. Thank you. My name is Brick Zivkovic. Last year, I presented a little bit about bioretention. My passion is still water quality, hasn't changed, but this year, I think we've really explored that and some of the feedback we've got from stakeholders. So just want to kind of jump into some of this analysis that we did, and hopefully we can kind of close the door on the water quality event. So real quickly, I kind of created a stormwater story. It's kind of involves some old people who wrote our criteria, but we can kind of jump through that. And so this is just a little bit of my presentation, and yeah, so really it all kind of starts as a long time ago in a galaxy far, far away. So let's call this 1970s, 1980s. We didn't really consider the idea of the water quality event. As we get into the early 1990s, these Jedis, we'll say Guo or Bonus and Tucker. I mean, that's where the whole stormwater story was going to go, but they kind of saw the need for this idea of a water quality event. And so not specifically the water quality event, but more so a water quality capture volume. So understanding that water quality impacts our streams, rivers, and what can we do to kind of influence that. And so this is kind of following the trend. The one thing I don't think I included in here is the 2012 water quality COSM, but just kind of where we started and how we got up to where we're at right now. And so 2021, 2022, I think we can officially close the door on this saga. So real quickly, some of the questions are understanding why. So why do we do this? I think the big things here is that we use design storms, but stormwater control measures, as the industry has changed, we've learned that there's more than just volume-based design methods. There's also flow-based methods. So right now, the way that the permit works, and this is really a generalized version of it, but we have a volume-based or a retention-based standard, which kind of is the runoff reduction water quality capture volume. But then we also have this treatment-based standard. So just real quickly, by a show of hands, how many of you have designed a stormwater control measure? Okay, now keep your hands up if you have designed a stormwater control measure for the treatment standard, specifically the pollutant removal standard. Only a couple of us. And so I think we can all kind of see there's this missing gap right now between a volume-based and kind of the flow-based areas. And so where this is going, kind of understanding that flow-based SCMs, so stormwater control measures, I'll jump through a couple acronyms, that's on the next slide, but really kind of their efficiency is not volume-based. Things that the concentration coming in, the flow coming in, for example, a hydrodynamic separator that operates at a certain condition to actually remove sediments. So understanding that there's no volume elements to this, but we only have a volume equation. So some designers will use the 2-year, other designers will use different types of service or flow rates, but even for the people that I've talked to out in the hall right now, some folks have said, hey, I've explored this, I've tried to back calculate the water quality capture volume to all these different storm events, peak flows, and they struggled, and I struggled too. But I think we've officially closed the door on some of the stuff that we've done. So real quickly, kind of jumping back, just to change our mindset real quick, let's think about some of the terms that we're talking about. In our criteria manual, we're very specific about understanding these different variables and how they influence us, specifically sedimentation. We can go through infiltration. I don't need to jump through all of these, but really I think kind of taking a step back again to not only just the terminology, but also the acronyms that we're introducing. So you'll see here that there's stormwater control measures, which will kind of align with the new criteria manual and updates, manufactured treatment devices, which is a new type of stormwater control measure, and then also these 3 things at the end. And so the second one, the water quality event, we'll jump into that definition right next, but I think that it's very clear to understand that all 3 of those at the end, they're intertwined and interlap, but there is very distinct differences. So what do we mean the water quality event? So we're not talking about the level of service event, and I think that this newest version of the definition of what we mean by the water quality event is not just the design storm. So for our region, 80 percentile, 0.6 inches, we're all familiar with this value. But thinking about the water quality event at a given site, the water quality event is different at each site. The depth of 0.6 inches might be the same, but the site characteristics, the design storm characteristics, other elements that will contribute to that actual flow rate. So really the water quality event is the 0.6 inch rainfall depth separated, and then also the corresponding flow rate for that smaller storm event. And so this is kind of the analysis that we looked into. Jumping back just real quick into some of the criteria stuff, I mean, the water quality capture volume and how this was originated by Dr. Guo and all those other researchers back 20, 30 years ago now, but just kind of how that's expanded into really what we're talking about here. We're talking about this 80 percentile event. So the majority of the storm events, well, not majority, but on any given day, this type of analysis will show that like this is really the range in which we want to capture. So what happens when it's less than that? Well, that's kind of the question, I guess we can say. Right now, we only have 2-year level design storms, but kind of just moving ahead and thinking a little bit more about like, what are we talking about here? I think that the presentation, the one environment earlier this morning was really a good reflection of this, as well as Mary's presentation. But really kind of, we're talking about the flow regime here. We use one design storm to define all of this, and we expect the best ecological integrity, but yet the magnitude or the frequency of these storms that we're really trying to target does really vary. And so I think that quote, the definition, kind of what is a natural flow regime, we're not just trying to carry it through river ecosystems, but now we're also trying to incorporate it into these kind of buffers, so the stormwater control measures before water gets discharged into those systems. So with that being said, kind of changing the frame set in our mindset, just kind of jump into some of the analysis. So really, I think the challenge here was for the amount of data that we analyze, I'd say at least 1,000 years of rainfall data, kind of thinking of all the different gauges and where that went to, as well as kind of the CUHP rational runoff. This is kind of the summary of the water quality analysis. So I can go through some of these pretty quickly, but ideally we took a bunch of different gauges and we performed very similar analysis to really looking at rainfall only. Is it possible to determine a design storm intensity, like something that's reasonable that would correlate with this? One of the things that we are seeing with some of these IDF curves, or not IDF curves, but really just kind of looking at the rainfall, is that the water quality capture volume, whenever it was originally developed, we used one data set with a given set of parameters, where we kind of assumed a separation time, assumed a minimum storm event, but kind of expanding that analysis and taking a step back. So we went to the original data set, we took original data, plus we've added a lot of other data to really kind of reanalyze this and understand what sensitivity is. So looking at rainfall only, we were like, well, can we get a peak 1 hour intensity based on a storm depth? So truth is, this is a bunch of different rainfall gauges over the course of, these are all alert gauges here, but what we're showing here is the peak 1 hour intensity on the y-axis, and then on the x-axis is the total storm depth. Not seeing too much of a correlation. Now let's look at that again, maybe versus the storm duration. Still not too much of a correlation. So really kind of with all this analysis, we weren't seeing too much that was really distinctive. But one of the things that this rainfall analysis, which was an iterative process between a rainfall only and then the rainfall runoff, which I'll touch base in a second about, is do our storm events that we're actually looking at, these smaller storm events, follow the same type of distribution? So that was one of the checks. And so the work that Dr. Guo and myself carried out was really kind of taking all of these storm events and normalizing them. So kind of putting the precipitation over the total precipitation and then the time over the total time. And so what this does is it gives us an axis of 1 to 1. And really, you can see the dark black lines on this axis. Those are kind of the shape of the curve of our regional design curve that's already presented in the manual. And so looking at all of these smaller storm events, were we able to see that, yeah, for the most part, most of our storm events do follow these trends. So at least we know that the distribution is somewhat reasonable. So we did this, performed it at a bunch of different gauges. I think the big thing to show is that, I'm gonna go back one. It's those areas that we see on the left side that fall outside. Those are the really short storm events where you might get 0.6 inches, maybe all 0.45 of that 6 inches fell within the first 10 minutes. So it's like, those are the areas where it's coming out. But for the most part, what we did see is that regardless of location or geospatial, or regardless of location, data set, which not only, all different data that we've analyzed, some rain gauges reported hourly, some others reported sub-hourly, so I think it's like, it's really good to see that regardless of the data set or these different parameter reporting intervals, we were still seeing similar trends. So yeah, real quickly, here's the summary. Kind of some of the things I think that we saw was that no real storm intensity unless you kind of start doing this real selective storm event binning, and I think that's almost cheating statistics in sometimes. But really kind of the storm event database that will be used again in the future. So that was part A. Now part B is we're looking at runoff too. So with the rainfall runoff analysis, I think this is probably what the most important part of the analysis is There's a couple different methods that the criteria method poses. These are really CUHP, swim. There's also the rational method too. And so really what I wanted to do here, and this is kind of stemmed from other research in the past, the runoff reduction method, but was looking at these different storm events and how they really compare. Because if we put something into a CUHP model and we put something into a rational method model, the flows at which that we're talking about are definitely really important, especially if treatment is based on those flow rates. So how do we convert this water quality event, this 0.6-inch depth, which has been held true through the analysis with the two different methods? So for those that know me, I like doing data and I like really the sensitivity. I'll find the ends and bounds of certain things. So for those that have ever run CUHP, the R values, really starting with those R values of how do we model that sensitivity. And so these are the different scenarios. So on the right side, we can see the CUHP input parameters. So for one model, there's 75 CUHP runs. So comparing the one model that we have, there's like 1 acre imperviousness. You can modify the length to centroid, kind of varying those parameters. And ultimately, what do we find? So the first thing that we found was, this is taking a step back. This is going into the IDF curves, but it was kind of part of the rainfall analysis specifically. The water quality event, where does that fit using the intensity, duration, frequency equation that we have? It's kind of corresponding to, depending on your location, just under the 1 year or probably right about the 1 year. So that value right there we can already see is kind of regionally, it's appropriate. It's something that's kind of under the 1 year. However, I think probably what's most important is whenever we start to look at that intensity compared to the different outputs. So what I'm showing here is the CUHP and rational method results plotted on one graph. We know that the rational method only produces one peak, and so that range of peaks that we're seeing there, the very top is assuming that really short time of concentration, so the 5 minutes, versus something that kind of falls within the lower bounds. But I think it's pretty apparent that we're seeing and then all of the lines represent all of those different CUHP runs. And so trying to compare the peak results between these two analyses, what we can see for the 1 acre, 100% imperviousness, or 100% impervious site, is our peak flows for the rational method are overestimating. It's what the criteria says, it's still what it says in the rainfall chapter. Those blue boxes are really something sometimes. So I think that kind of looking at that as well as like not just the 1 acre, but also varying these parameters as other, varying these parameters with acres as well as imperviousness and kind of really trying to look at this range. What we can see collectively is that the rational method, once we start, for these smaller storm events specifically, the rational method is very much overestimating some of the things that we're finding. I think that really the key differences that we see here are 1, design storm characteristics, 2, drainage area characteristics, and then 3 is that imperviousness runoff relationship, because all of those are really directly correlated with the actual peak flow that we're getting, especially from the rational method. So really design storm characteristics, I think this is one of the first settings I guess we can talk about, because really what we're doing in hydrology with all of these is we're tweaking different settings. And I think at one point we tweaked a setting and it's worked for the most part, but now we're kind of figuring out that it's still limited in some other factors. So between that, the rational method, if we just look at design storms, we're assuming an average intensity versus something that's regionally distributed. And then also our storm event depth that's actually been regionally calibrated and quantified. As opposed to something that's intensity-based and we're just assuming a time of concentration equals the storm duration. So we can already just see that there's some differences between the two. Next is drainage area characteristics. I think that this is something that we'll see, 1, for the new criteria, but understanding what the hydrologic design point is. If it's going into the upstream portion of the basin, we want that design point, not the point at the end of the basin. It's still important, but like understanding that where the flows are coming in is definitely influences it. But then this is probably one of the biggest drawbacks to the rational method is it assumes nothing about the drainage area. It assumes uniform, homogeneous losses, other things like that, compared to something that's CUHP, which is shape-based, length-based. There's initial abstractions. There's a lot of these other things that are time-based in nature, which is what we're really trying to kind of find, as opposed to a single peak value. And then the last, I think this is kind of touching on the imperviousness. For those that know me, I comment on imperviousness. I think it's something that shouldn't be it shouldn't be left so much to engineering judgment whenever certain values are actually quantifiable. So certain things here that we're seeing, especially whenever it comes to the water quality event. Will pervious surfaces create runoff? Likely not. We're talking about these smaller storm events. So understanding what these directly connected impervious areas are is probably the most imperative to like really these types of flows that we're talking about. So I can touch a little bit more on this, but I think it's probably best to kind of jump back into the text. I think some of the findings that we found here from this analysis were definitely, they weren't new. They might have been restated or refound in a different way, but I think really touching base on some of these and the limitations of the rational method and what we're really using it for. And so, so kind of why does this matter again? I'd like to jump back into this one. So like MTDs specifically, one of the things that is their removal efficiency, this is just for one example, is it's based upon device characteristics, storm discharge, water temperature, and influent characteristics, so the sediments that are coming in. But volume-based design methodologies can't really be applied for those types of designs. And so this comes from a study that was done a little bit over 10 years ago, but just understanding that this efficiency, not only efficiency, but the operation, they operate based on flows. And we really only have a volume-based equation or a different type of level of service equation that we're going to be using for something like this. And so understanding that intent and really speaking towards the accuracy, which if we're trying to remove to the pollutant removal standard, we need things that are accurate versus something that's conservative where if we're assuming this value, we can store it, it's conservative because we know if it's more than that, we're still conservative. So I think those are really the kind of the big key hitters. And so these recommendations, they're still in draft, but kind of based on some of the analysis and feedback from a lot of the analysis that we did and what do we do with this in the end. So thank you, Andrew Earls, too, for that, and Dr. Guo, but kind of this feedback of how do we implement this into our criteria. And so with the newest criteria, we'll see, or newest version of the Chapter 4 later this year, maybe early next year, kind of this new water quality event analysis, which will be incorporated into the front sections as well, Chapter 6 of Volume 1, but kind of a peak flow and a method to quantify that peak flow. If you put in the water quality event depth into the rational method, you might be overestimating that removal rate. And for an MTD that's going to operate at certain efficiencies, if we're looking at the lower efficiency, anything less than those 80 percentile storm events, or whatever we're designing for, it's never going to operate effectively. So we're going to be missing all of those smaller storm events because it's a flow base that's just we're not going to be able to capture it. So I think kind of with that, looking ahead, we're actively working on the technical memorandum, which will be published soon. So if you're interested in more, or kind of want to figure out more about that analysis, and then kind of some updates to the U.S. Storm Drainage Criteria Manual. Specifically, you'll see some new MTDs and modified fact sheets. The water quality event will also be incorporated into Chapter 6. And so with that, that's everything I got. So.